Okay. ADM 3, Lesson 9, Basic Properties of Similarities. So what we're going to do in this lesson is we're going to show a rule or explain a rule that basically describes that, and I said in the last lesson that we're going to prove that two triangles are similar if the ratios of their sides are constant. And that's going to be actually saved for the next lesson. In Eureka Math in Lesson 9, what we talk about is saying if one triangle is similar to the other, or one shape is similar to another, then that second shape is also similar to the first. And that kind of goes without saying. It seems obvious, but we're going to try and touch on that. The second thing we're going to do is we're going to say, well, if one thing is similar to another thing, and that other thing is similar to a third thing, then the first thing and the third thing are also similar. We're going to actually do an exercise in that. And that's also something that you did in class today, exploratory challenge number 2. If you did it and well understand it, you might just skip by that one. The last thing we're going to do, and it's kind of key, we're going to do homework help. We're going to do that. The homework problems ask some interesting questions, and they kind of go back to what we did a while ago in this unit. And so I'll give you some of that. And then we're just going to also solidify some of our knowledge about dilations and rigid transformations. And we're going to go through the exercise of taking some triangles and doing some rigid transformations and dilations to prove similarities. And so we're going to kind of go through some of that fluency and some of that stuff and practice some of that stuff that we've been learning, and just make sure that we really get a good grasp on how we dilate something, then rotate or translate it into another shape. Okay, so that's what today's all about. Just a little bit of solidification, understanding some rules that may seem a little bit obvious, but let's just get on with it now. Okay, let's cut over to our sketch pad and just get right on it. Whoops, let me make this sketch pad the right size. There we go. All right. Okay. There we go. All right, sorry about that. All right, so now the 2 keys for today, as I said, and you can write these in your notes, is that if a triangle is similar, right? This symbol here means is similar. Is similar to. That's this little squiggly sign here. A second triangle. And you can also just say it in general. If this means if shape 1, shape S, is similar to shape T, right? So this could be a quadrilateral. It could be a pentagon. It could be an octagon. It could have 5, 6, 7, 4 sides. It doesn't have to just have 3 sides like these triangles. Then the second triangle, or the second shape, is similar to the first shape. So that's one key learning from today, and you need to know that that's true. And the second thing says if we have, and this is different than the first one, this says if we have shape 1, shape 1 is similar to shape 2, and shape 2 is similar to shape 3, then shape 1 is similar to shape 3. And that should make sense, because if we take a shape and we do some transformations and dilations on it to get to shape 2, and then we take that shape 2 and we do some transformations, some rigid transformations and some dilations on it to get to shape 3, then we should be able to do some set of transformations and dilations to get from shape 1 to shape 3. And in fact, those would be the exact same dilations and transformations that you used inside this first similarity and the second similarity. So if you just kind of mimicked what you did to get from shape 1 to shape 2, and then again from shape 2 to shape 3, you could have done that, and you'd get from shape 1 to shape 3. So that's kind of what that says. And we'll go through an exercise that kind of proves all that. So the one thing I want you to recall also is that if two objects are similar if I start with one and just perform dilations on it and transformations, which are, again, translation, that means move, reflection, which means to mirror, and rotation, which means to twist. If I do dilations and then these three other operations on the starting object and I end with the second object, then those two objects are similar. Okay, so let's go through an exercise that we did today, that you did today in class, and that is this one. So this was challenge number 2, I think. And the idea was to take this first object, and we're going to try and show that it's similar to the second object through a series of dilations, or a dilation, one or more, and then 2 transformations to get to object 2. And then, so this is triangle, ABC to triangle A prime, B prime, C prime. And then we were going to do the same thing from triangle ABC to get to triangle A double prime, A B double prime, C double prime. And that's this one. And so we wanted to show that we can go from here to here and then go from here to here. And then the idea would be, can we go from here to here, which basically is the proof that if one thing is similar to the other, and that first thing is also similar to a third thing, then the other two things must be similar to each other. So that's the exercise from today. So let's just look at this. So let's recall how we dilate objects. Okay. How do we dilate objects, or how do we dilate and transform an object? Now, remember that if you dilate an object, it's the same thing as dilating an object, dilating a shape is the same thing as dilating each vertex. And to dilate each vertex, you just take each point, you take each point, x, y, and dilate it by multiplying by scale factor. By multiplying each coordinate by the scale factor. So if you took x, y and multiplied it by the scale factor, you would get rx, ry. So let's watch how that happens. We're going to do it once or twice, and then I'm just going to assume that you've learned what we've taught. And now we've done this before. This is not new. This is not new. This is a reminder. So if I take this point here, right, and I want to dilate it. Now the first thing is, let's think about how much bigger is this shape than this shape? How much bigger to go from here to here? Well, let's look at the short side and figure it out. Well, the short side here is 1. This short side here is 3. So I have dilated with an r equal to 3. So I want to dilate this triangle here, and watch what happens when we dilate each point with an r equals 3. Let's do this new thing in like dark red, so we can see what changes we've made. Okay, so now this point here, down here, C, this is point C, and it has coordinates of -3, 0. So if I want to use an r of equal to 3, because I'm making it 3 times bigger, my C prime, or my new point, is going to be -3 times, or 3 times -3, comma, 3 times 0. And that's going to be -9, comma, 0. So watch this, see. So -9, comma, 0. So -9, comma, 0. So I've dilated it. Remember, we dilate about the origin. That point is going to be right on this line. And it's going to be 3 times further. So there's my 3, and there's my 3, and there's my 3. So it works out. So our formula of multiplying each coordinate by our scale factor does indeed get us this correctly dilated point. Now we're going to dilate point B using the same technique. Well, B is -3, comma, 1. So now we have to do 3 times -3, comma, 3 times 1. And we get, for our new dilated point, -9, comma, 3. Remember how this works? And we're going to end up with a triangle that's got each side is 3 times bigger. So let's dilate our point A. Well, our point A is -1, comma, 2. So we have to take our 3 times our -1, 3 times 2, and we get -3, comma, 6. -3, comma, 6. So let's see what happens with our triangle. Okay, well, it looks to me like we have a triangle that is 3 times bigger. And that's using our cool formula. And this is something that we learned earlier. And notice now that we have our 2 shapes that are indeed the same. These are the same size. They are the same size. Okay, so now we've done a dilation. Now we have to simply do a transformation. And what kind of transformation can we do? Well, they're already twisted in the same direction, so we don't have to do a reflection, nor do we have to do a rotation. We can simply just move this guy up. And how much do we have to move it up? Well, we have to move it up 1, 2, 3, 4, 5. And if we move this one up 1, 2, 3, 4, 5, and this one up 1, 2, 3, 4, 5, we actually have a triangle that is right on top of each other. So to get from triangle, let's just sum up what we did. To get from triangle ABC to triangle A prime, B prime, C prime, we had to 1, dilate with an R equals 3, and then 2, we had to translate up 5 units. And so we have proved that triangle ABC is similar to triangle A prime, B prime, C prime. Now, to prove that triangle ABC is similar to triangle A double prime, B double prime, C double prime, we need to go to GeoGebra. And the reason is because this tool here doesn't let us rotate very well, but GeoGebra does a really good job of rotating for us. So let's go over to GeoGebra. And remember, the key is we're going to take this first triangle here and we're going to dilate it, and then we're going to do some transformations to get to our second triangle. Okay, here we go. There you have it. We have our same triangles right here. So let's look at getting from here to here. Well, remember, the first thing we want to do is we want to do a dilation. And we need to know what our R is going to be. Well, let's look again at the short side and see how much that has to be dilated, because that's going to be our dilation number, our dilation constant, our scale. So again, if this side is 1 and this side up here is 2, right? Our dilation constant is what? How much did we have to blow this side up by? Well, it's R equals 2. So to get our new points, we're going to have to take each factor and we're going to each coordinate and we're going to have to multiply by 2. So let's do that. So here we have, well, we can just write it down. Let's just write it down and do our math right now. So we have to take -3, 0, and we have to multiply each coordinate by 2. We have to take -3, 1, and multiply each coordinate by 2. And we have to take -1, 2, and multiply each coordinate by 2. So we get, why don't you try it? See what happens when you multiply each coordinate by 2. Where should our new vertices be to dilate triangle ABC? I hope you tried it. Hope you paused and tried it and just wasn't waiting for me to tell you the answer, because you're going to need to be able to do this and demonstrate this on future tests and future assessments. But this will be -6, 0. This one will be -6, 2. And this will be -2, 4. Right? We've just multiplied each thing by 2. So let's make our new points. Here's -6, 0. Here's -6, 2. And here's -2, 4. And we can make our triangle out of that. And we have a triangle now that's the same size. Notice the short side is 2, and it looks to be about the same size. So now what are we going to do? How are we going to, whoops, let's go back to this. Okay, so now what we got to do, remember back, this is going to go all the way back to lesson, even 8M2. Remember how we show that two triangles are congruent through rigid transformation. We want to get this triangle. Just a second. Let me see if I can get this thing straightened out over here. Oops. Okay. Well, we want to take this triangle here, and we want to translate it into, or to transform it into this triangle. Well, the first thing we want to do is we want to transform one point. We want to transform the triangle so that one point is right on top of another point, right? So how do we get, what's a good point to match up so that we can just move it straight over to here, right? We want to match one point up. Why don't we match up this after this A double prime? Because we can just, if we just translate, right? If we just translate this guy, this triangle here to the right, 6 units, right? Or 5 units, 1, 2, 3, 4, 5, then this will be straight on top of this one. And then we are only a reflections and rotations away. If you recall all the way back to 8M2, that's our strategy for proving that two triangles are congruent through rigid transformation. So let's translate. So the first thing we did is we dilated with R equals 2. Now we're going to translate to the right. I'm going to translate to the right 5 units. So we're going to say, and I can just do this shorthand. Watch what I do. I say translate. Well, let's make our vector that we're going to translate it by. Let's just graphically represent what we're doing here. So here's our vector, and we're going to translate this 5 to the right. So let's just make a vector that's 5 units to the right. Right? So this represents moving something 5 to the right. So let's go over here, and we're going to say translate our new shape that we just dilated. Let's just translate it to the right. So notice this new triangle that we have. What happened? What? Oh my goodness! What are we doing? What are we doing? Sorry about that. Let's just get this all back kind of to where it was. Okay. Kind of back to where it was, maybe a little bit. And we're going to say translate poly 4 by U. Okay, so now we have our new triangle here that we've translated. So we've dilated this triangle up by 2, and now we've translated it to the right by 5. Now our next move, if we just kind of think about swinging this thing up, we're going to rotate this thing around point A double prime, and we're going to do it. We're going to do it a certain amount. We're not sure exactly how much, but we'll make a slider, and we'll make a slider that's going to help us do that. And I'll show you how we do that right. Taking the shape and we're just rotating it around that point. Can we get it on top of that other point? And the answer is yes, with a rotation of 270 degrees. I'm sorry that took so long to set up, but we did 3 things. So if you recall, what did we have to do in addition to just bearing with me through this craziness? The first thing that we had to do is we dilated it by 2. The second thing we did is we translated it to the right by 5 to get from this triangle to this triangle. And the third thing we had to do, is we had to rotate it by 270 degrees about point A double prime, right? Kind of cool. Woo! There we go. So the thing that, so we what did we do in summary? We took ABC and we dilated it, and then we translated it to get to triangle A prime, B prime, C prime. Then to get from triangle ABC to A double prime, B double prime, C double prime, we realized we had to dilate it to get it up to the right size. Then we had to translate it, and then we had to rotate it. But again, we did a series of rigid transformations and dilations to match those two up. Now, the third exercise would be to take this triangle, A double prime, B double prime, C double prime, and then map it or show that it's similar to A prime, B prime, C prime. And what I'll let you do is I'll let you do it. And I'll give you the hint that you use an R factor of 1.5 because the short side here is 2, and the short side here is 3. So you're going to need to multiply it by 1.5 of dilation, and then you're going to need to translate it. You're going to need to move it after you dilate this smaller triangle by 1.5. You're going to have to move it, and you're going to have to line up your new wherever C double prime ends up onto C prime, and then 3. That's step 1. That's step 2, and then step 3. You're going to need to rotate it. Now you can rotate it using, GeoGebra, or you can do it using your tracing paper. Remember, that's how we did our rotations in section 8M2. Now I'm going to cut back over here to the sketch pad, and I'm going to give you some homework help. So here's the key. You're going to have problems that look like this. Given these two triangles, in this case you have A, B, C in triangle A double prime, B double prime, C double prime. Can you show us that they are similar using only dilation? Can you do it using only dilation? And the answer is going to be interesting because you can't. The thing is if you want to dilate point A double prime into A, because we're going to have to do a dilation. Remember that all of the points, if all you need to do to show similarity is use dilation, and sometimes you can, then you should be able to draw line through each set of dilated vertices, and they should intersect at common point. Parentheses, usually the origin, but not always. Usually the origin. Okay, so let's do that exercise right now, and let's see what happens. So I want to take point A down to A double prime, and I want to see, I'm going to see if I can make all of my points line up. In other words, can I just dilate that smaller triangle and get the bigger triangle? Well, let's go through A. Let's dilate our point. If I was to dilate C double prime into C and B, and the answer is no, because these lines don't line up. They're not coming to a single point. So I can't just grow this object and get this second object without having to twist it or move it or do some other rigid transformation. And that kind of makes sense. If I just make this guy bigger, if I just make this small triangle bigger, I'm going to end up with a triangle, that looks like this, and it's not going to be in the same orientation as this other one. So the answer is no. I'm not going to be able to do it. No. I will also need to use rigid transformations. And probably you're going to need to use, for example, you're going to need to use rotation. It's clear to me that you're going to need to twist this guy like this to kind of orient it like this one. Now let's look at a different problem. Let's look at a different problem. This one. Now these look like they're in the same orientation, and they look like they're, maybe I could just dilate this guy up. Let's look and see. Let's look and see. So I'll take the big one down to the small one. I'll take B through point B. And I'll take C back through C. And notice, I can, in this case, I will be able to just dilate this guy up, right? I'm just going to take each point dilated about the origin and go here, go another one, and go another one. In fact, I can kind of tell what my R is. What is my R? I'll ask a little follow-up question. What is R? My scale factor. My scale factor, what is R? Well, this is 1 unit, and this is 3 units. So I have used a scale factor of R equals 3, right? And so my A point here, let's just go one step further. So my A double prime is at 1, 2, right here, 1, 2. My B double prime is at 2, 1. And my C double prime is at 3, 2. And if my R is 3, I should be able to multiply each coordinate times 3 and get my new coordinate. And so my A would be at 3, 6. And it is 3, 6. And my B point should be at times 3 times 3, I get 6, 3. And it is. And my C point should be at 9, 6, or 3 times 3 and 2 times 3. And it is. So the answer here is yes. I can show dilation. I can show similarity with only dilation. Okay, so that was a lot. That was definitely, a lot of information, a little bit of gnarly work that we had to do to show similarity between a smaller triangle and a larger triangle, especially when we couldn't just dilate it. We had to dilate it, translate it, and then twist it. But boy, if you can do that, you are on top of the game. That is really the essence of being able to think through a problem, really think geometrically, and understand the concepts of similarity, being something that's the same shape but a different size and a different orientation, but just shrunk down and then twisted and moved around a little bit. So hopefully this was a useful exercise for you. Hopefully the homework helped. Ask any questions if you need any questions, or let me know if this was useful to you. And otherwise, thank you. Thank you. Oh, double tail. Wow, great big crowd. Thank you. I will be back for lesson 10, and we will keep going with similarity on unit 8 and 3. And I love teaching you guys. So give me feedback, and I will do my best to give you exactly what you need. Bye till next time.